Well, good evening, ladies and gentlemen. Let's try that again. Good evening, ladies and gentlemen. That's much better. Welcome to the National Air and Space Museum. You've already heard the warm-up, so I don't have a big job before me tonight. My name's Roger Lanius. I'm Associate Director for Collections and Curatorial Affairs here at the Smithsonian's National Air and Space Museum. It's my pleasure to welcome you to this Exploring Space lecture. We have a very special evening before us, no question about that. Dr. Robert Smith is a member of the History Department at the University of Alberta. He's going to present on a great topic with a great title, the Hubble Space Telescope, the Agony and the Ecstasy. As we all know, the Hubble is a most significant scientific instrument. Some would say maybe the most significant ever built in astronomy. We can debate that if you wish at some point. But its operational lifetime has been met with all kinds of ups and downs. There's no question about that. How it was nearly canceled before it was even built, the difficulties associated with its deployment and it not working properly in the initial phases. And then, of course, a stunning set of successes in the years since the mid-1990s in which it has really revolutionized what we understand about space and the universe beyond. And Dr. Smith is uniquely suited to lead us through this particular discussion. He specialized in the history of science, especially the physical sciences, and beyond that, especially the history of astronomy and cosmology. And he is a well-published and accoladed given, how's that for a phrase? Historian. His Space Telescope book, a study of NASA, science, technology, and politics, won numerous awards. He has written many other books, including one with David Dvorkin, our own David Dvorkin, who was up here earlier, called Hubble Imaging Space and Time. He's got current projects underway relative to the James Webb Space Telescope and a biography of astronomer and a cosmologist, William Hunter McCrae. Now, every museum activity that we do here has to be sponsored in some particular way, and so I would like to recognize the two sponsors for this evening's lecture, and that is Aerojet Rocketdyne and United Launch Alliance, and please, let's give them a hand. To these two organizations for their support for this lecture, and for the representatives who are here from those organizations, thank you personally for all that you've done for us. Through this collaborative process, we are helping to bring understanding to the larger society about this universe and about our place in it. It is my pleasure to welcome to the stage Dr. Robert W. Smith. Please welcome him now.
Well, we're celebrating this year the 25th anniversary of Hubble in space. And so I've given a number of talks on the history of Hubble. And I always feel a bit like somebody who's been invited to a wedding anniversary party for a couple who've been married 25 years. And everybody's saying, oh, it's all been great. It's all wonderful. And then I want to say, no, no. There were really rocky periods. Things nearly didn't happen to begin with. And even when things did happen, it looked like it was all over. And there was the ultimate triumph in the end, but things were never nearly as clear as sometimes they look from our perspective of 25 years in orbit, when everything looks inevitable, it's all straightforward. And so tonight I'll be arguing that it's not, which gets me to my title, The Agony and the Ecstasy. And some of you may not have seen Charlton Heston as Michelangelo in the 1965 movie. And what the movie is about is the painter Michelangelo, who is supposed initially to be building 40 statues for the Pope's tomb. But the Pope changes his mind and he wants Michelangelo to do some painting, and Michelangelo doesn't think he can do painting anymore. So he's in agony. But eventually he gets his act together and paints a Sistine Chapel. And it takes an enormous amount of time to do it, but in the end he succeeds. So he moves from the Agony to the Ecstasy. And there are echoes of that, I think, as you will see, in the history of the Hubble Space Telescope. But first, let's go to the White House. And it's the White House of Gerald Ford. And you would have to be a political junkie, I think, to recognize the two other figures in there. That's James T. Lynn. He was the director of the Office of Management and Budget. And that's Guyford Stever, the science advisor to President Ford. And at this particular meeting, they were there to discuss the budget for NASA. And Stever's normal job, as he told me in an interview, was he would go in and say, well, I know things are tight, but this is a really worthwhile project. Or the science promise from this project is going to be very exciting, so I think we should really try to fund it. But at this particular meeting, President Ford and James T. Lynn were enthusing about what it actually meant to look back into the far universe, to see the light from galaxies that's been traveling towards the Earth for billions of years. And so at that point, Stever decided, I'm going to shut up. And the White House was, in fact, very supportive of what would be later called the Hubble Space Telescope. And when, in 1995, the Hubble Deep Field results came back, which you heard about, I think, at the last of these lectures, I couldn't help but think about Gerald Ford and the meeting with Stever and James T. Lynn, linking to the actual findings some 2 decades later. And what we'll see is that the history of the Hubble Space Telescope reaches up to very high political levels on a number of occasions in that history. So, with that as a kind of preamble, let me explain what I'm going to do. I'll talk a little bit about why is it the Hubble Space Telescope, why is it not the something else space telescope. I'll talk about the location of telescopes in space and Hubble. I'll talk about a famous problem that occurred with Hubble that was discovered shortly after its launch, and that was what astronomers know as spherical aberration. And for a time, spherical aberration filled up evening news shows. It made late night comedy routines. And I'll also talk about the cancellation and then reinstallation of what was the 5th servicing mission in 2009, because those 2 episodes, I think, both tell us a lot about the history of Hubble. And then what I'd like to do at the end is try and imagine ourselves forward in time to 2090. And we're reading a textbook, or maybe we're looking at our Kindle device, or whatever it is we're using in 2090, an American history textbook, or maybe a history of science textbook, and what will it say about the Hubble Space Telescope as people celebrate the 100th anniversary of the launch of Hubble? And I picked 2019 in part because it's sufficiently far forward that nobody can ever say, you were wrong. So, let's give a little bit of astronomical background. Why is it the Hubble? Well, if you'd have been here at the Smithsonian for electron astronomy in, say, 1905, you would have been told that the universe consists of our own stellar system, and there are nebulae around our own stellar system, the system of stars, but that's it. That's the entire visible universe. Maybe there are other galaxies to be sighted, but nobody, not even the possessors of the biggest telescopes, have ever seen these other galaxies. So that was the visible universe. And here's an object which I think is probably familiar to many of you if you've been outside far away from city lights and looked almost straight overhead. In the fall, you will have seen this object, most likely, the Andromeda Nebula, as it was termed at the end of the 19th century. This is a historic photograph from 1888. And when this image was shown, there were astronomers who exclaimed, "The nebula hypothesis made visible." And why was that significant? Because the nebula hypothesis pointed to the creation of our solar system with a central star born out of swirling dust and gas. And here, obviously, a planet's forming, right? It's perfectly clear. And that's at the very end of the 19th, early 20th century. Why did that view collapse? And that gets us to Edwin Hubble. Here's Hubble as a young man, a photograph taken when he was visiting family in Louisville. And that's a picture of Edwin Hubble at the Mount Wilson Observatory in California in the 1920s. Because he was trained at the Yerkes Observatory of the University of Chicago. And what Hubble did was to observe in unprecedented detail the Andromeda Nebula. And he used what was then the most powerful telescope in the world, the 100-inch telescope on Mount Wilson. And if you want to see how Hubble positioned himself at that telescope, go to Explore the Universe, the gallery just outside, where you can actually see a mannequin of Hubble observing with real artifacts from the Mount Wilson Observatory. And what Hubble did was to take photographic plates of the Andromeda Nebula, and he found in the Andromeda Nebula variable stars, Cepheid variable stars. We needn't go into the details of why you can use Cepheids or how you use Cepheids to get distances, but the key thing was by observing Cepheids in the Andromeda Nebula, he could find its distance. And this was in 1923. And he clinched, by working out the distance, that the Andromeda Nebula was way outside our own galactic system. It was far too big, impossibly big to be a single solar system in formation. So in 1923, what Hubble did was to transform this object, the Andromeda Nebula, into a galaxy. And he proved that galaxies exist in the universe and that, in fact, we are in a universe with a myriad of galaxies. Later, he and a colleague at Mount Wilson developed evidence for the motions of the galaxies, which other astronomers took as clear evidence for the expanding universe. And so for Hubble's pioneering researches in extragalactic astronomy, the Hubble Space Telescope was named after Edwin Hubble in 1982. And that's well before the telescope was launched. As we will see, the launch was in 1990. So that's why we have the Hubble Space Telescope. Now, in the 19th century, really powerful telescopes, and this was the most powerful telescope of the 19th century, were not built in particularly useful places, at least for astronomers. This is the famous Leviathan of Parsonstown. It had a mirror 72 inches in diameter. It was built in the middle of Ireland, and it was built next to a peat bog. And as one astronomer put it when he went to visit the observatory where the Leviathan was located, the weather is vexatious but not absolutely repulsive. And astronomers realized that what they needed to do was to go higher, to get up some mountains away from as much of the atmosphere as possible. And certainly it was not a very good idea to put state-of-the-art telescopes in locations where you would have to contend with so much in the way of cloud. So by the end of the 19th century, astronomers were going up mountaintops, and so this is the Lick Observatory in California at the end of the 19th century, and then we have Mount Wilson, where Edwin Hubble plied his trade for many years. And Mount Wilson is at about 6,000 feet, but even then, astronomers dreamed of getting higher, getting above the obscuring layers of the Earth's atmosphere. Could they escape from their location at the bottom of an ocean of air to reach a place, in effect, where the stars do not twinkle? And the astronomer on the left here is Henry Norris Russell, arguably the leading American astronomer in the early 20th century. And Russell, in 1933, wrote a column for Scientific American. And his column was called "Where Astronomers Go When They Die." And the conceit of the article was that if astronomers were well behaved in this life, they will be allowed when they died to take their telescopes to the moon. The point being that there's no atmosphere on the moon. And Russell is talking here to another astronomer who was trained at Princeton. This is Lyman Spitzer, and Spitzer is going to be very important for our story as we go forward tonight. Because Spitzer, in many ways, was the driving force behind the early plans for the Hubble. And Spitzer was interested even before World War II in the possibilities of telescopes in space. But how could you possibly get a telescope in space if you're thinking about these issues in the 1930s, where you don't really have a mechanism? But the developments in World War II, particularly the development of V2 rockets, convinced Spitzer now things were possible that had been impossible before. And in 1946, Spitzer wrote a paper for the RAND think tank called "The Astronomical Advantages of an Extraterrestrial Observatory." And there he pointed out what would be the major reason for putting a large telescope in space. Not to supplement present ideas, he argued, but rather to uncover new phenomena not yet imagined. And in the late 40s and in the 50s, astronomers sought lots of different ways to get at least high up in the atmosphere, like balloon experiments. This is an experiment that was conducted by astronomers at Princeton. Stratoscope, and you can see the astronomical payload here. Again, the drive is to get above as much of the atmosphere as you reasonably could. Sometimes rockets were combined with balloons. David's not allowed to answer this because he knows what the answer is, but what would you call this combination? A raccoon, exactly. So, splendid. Sometimes there were even astronomical instruments put behind the pilot of X-15s, and here we see an X-15 being launched from a B-52. But things changed radically in 1957 with the launch of Sputnik, because the United States responded in a number of ways to what was seen as the challenge of Sputnik. And it had always been the dream of astronomers not just to get above the atmosphere for a few minutes, as you could with a rocket, but to orbit satellites. And so NASA early developed plans for astronomical orbiting observatory. It's like this one. This is an observatory that was principally carrying instruments developed at the University of Wisconsin. And you get a sense of the scale of this from the technicians at work on it. And here are the solar arrays to convert sunlight into electrical power. But as well as what was called in the 1960s anyway, these unmanned spacecraft, there were also plans that relied on using humans in space to make astronomical observations. And this is a famous illustration from Collier's magazine in 1952, where we've got the famous space station design with a shuttle, and we've got a space taxi, and we've also got an astronomical telescope, because it seemed to planners and dreamers, like, for example, Wernher von Braun, that you could use a space station in conjunction with astronomical modules or units or telescopes. And so in the 1960s, there are a number of NASA plans to develop what is shown here as an astronomy module that would link up with a space station. And the two key figures in NASA in the 1960s in developing these ideas about what you could do in space with large telescopes were on the left, we have Nancy Roman. She was in effect the head of astronomy programs in NASA. And on the right, again, Lyman Spitzer. And part of their job was to interest astronomers in going into space, because a number of astronomers who used ground-based telescopes really were not at all interested in flying telescopes in space. They regarded it as very risky. Rockets blew up. Who knew if you all would maybe get no data back, having spent years building these instruments? And it was extremely expensive. The money, many of them thought, would be better spent on telescopes on the ground. And so Spitzer, in part, went around preaching, in a way, to these naysayers. And he headed a committee, for example, in the late 1960s that went to a number of universities and talked about what could be done with a large telescope in space. And the report that came out of that tour was called The Scientific Uses of the Large Space Telescope, but it became more colloquially known as Chairman Spitzer's Little Black Book, after those of you old enough to remember the Cultural Revolution in China, Chairman Mao's Little Red Book. This was Chairman Spitzer's Little Black Book. And so if we just stop briefly to say, well, where are we in the planning here? We've got Lyman Spitzer's 1946 RAND study. 1958, NASA has formed. Late 1960s, this push for what was called the Large Space Telescope, LST. And then in the early 1970s, serious planning actually gets underway for a large space telescope. And it engages lots of astronomers, contractors, as well as NASA staffers. Here's one of the early concepts. We've now got a mirror that's about 3 meters in diameter. We've got astronauts working, in fact, with scientific instruments at the back of this, upgrading it in shirt sleeves. The idea was that the astronauts would not be there permanently, but they would go and service and upgrade such an instrument. By the early 70s, this is the most favored design. It's a 3-meter telescope, again, large space telescope. 3 meter means the main mirror was 3 meters in diameter. But now, what do we see appearing? We've got the shuttle. And this was a major development in terms of the history of what will become Hubble, because this marriage of human spaceflight with astronomy was what was going to make the project particularly attractive to NASA, and in time, particularly attractive to funders. Here's another concept with a very early idea of the shuttle linking to a planned large space telescope. But now this is the key problem that the astronomers, NASA, and the contractors faced. And it's well expressed in this BC cartoon. Can everybody read the legend okay? So, are we going to discover the secrets of the universe? The key is not ours to have. How come it ain't in the budget? And this, in fact, was the first item that President Ford saw at that meeting I talked about at the very start of the talk. So it was sitting in his briefing book he opened his NASA briefing book, and here was this cartoon. So, how to win the support of the White House and the Congress. In the early 70s, NASA's principal interest was in the shuttle, and here we can see President Ford. That's then NASA Administrator James Fletcher, and there's a model here of the shuttle. But from the White House's perspective, Hubble, or what would become Hubble, was attractive for a number of reasons. Why invest so much money in the shuttle unless there are worthwhile payloads to put in the shuttle? So that was an attractive reason. It would demonstrate US leadership in science and technology. Ford was also concerned that R&D spending, if you looked at the overall aggregate of research and development spending, was going down. He wanted to get it going back up. And also he found, as we saw earlier, the science to be attractive. But in the Congress, there was a great concern about priorities. And this was well expressed. This is something that Lyman Spitzer told me in an interview. He was facing congressmen who'd funded other telescopes, yet now astronomers were coming back for a different one. What was going on? And so in the early 70s, astronomers had not really done a very good job of explaining the differences between radio telescopes and optical UV telescopes like the Hubble. So that meant that there was a lot of education and advocacy that had to go on. And for the astronomers, the two key advocates were these gentlemen, Lyman Spitzer and John Bacall. Bacall was from the Institute for Advanced Studies at Princeton, and Spitzer was at Princeton University. But they became leaders, really, of a very large group of astronomers. And this is the first time this happens, that you have many hundreds of astronomers involved in a campaign to win support for a large project. It involved people like, for example, Margaret Burbidge, who was the president of the American Astronomical Society, who worked the halls of Congress. Previously, astronomers let the leaders of their community do this kind of advocacy for them. But under the guidance of Spitzer and Bacall, then astronomers really made this into a grassroots effort. Other allies were brought into bear, including Superman. And again, this is not a spontaneous outpouring of Action Comics. This is the result of somebody calling up Action Comics and saying, wouldn't you like to do a story on the Large Space Telescope? And here is, of course, the Large Space Telescope. So there was a period, a 3-year period, 1974 to 1977, where there are lots of supporters who had to fight very hard in a kind of loose coalition to win support for what would become Hubble. And there were significant changes as a result of this. The Large Space Telescope, which had a 3-meter primary mirror, became the Space Telescope. Large implied extravagance, according to the NASA administrator, so the large was dropped, and it became Space Telescope, and now the primary mirror was 2.4 meters in diameter. There were 5 dedicated scientific instruments, although with the Space Telescope, the fine guidance sensors also function as a 6th instrument. On this Large Space Telescope, there were 7 scientific instruments. This was going to be in a purely American effort. The Space Telescope was going to be a collaboration between NASA and the European Space Agency. And so approval, though, was won in 1977. And here we can see the basic concept. And normally I go on in lectures about how the Hubble is roughly the size of a yellow school bus. Well, I don't have to do that tonight because on the way out you can just look to your left and see the mock-up of the Hubble in the gallery there. There are a number of scientific instruments, all designed to be replaceable in orbit. And so that was the basic concept of the telescope. It's also worth pointing out that the location of Hubble near some of the reconnaissance satellites out in the gallery is also, I think, quite appropriate, because really the earlier history of space astronomy is not that important in technical terms anyway for Hubble. Hubble's technical heritage really owes most to the world of national security, and in particular reconnaissance satellites, and it would have surely been a vastly more expensive project to do without the construction for other purposes of a lot of the institutional and technical base. And that point's made very clear. This is President Reagan's science advisor, George Keyworth, who in 1985 pointed out that Hubble was new, certainly new, but it draws on technologies used in military systems. So, for example, this is Moscow, and the image on the screen does not do justice to the resolution here, but here we've got the Kremlin from the Corona reconnaissance satellite, and there's an example of Corona again out in the gallery. So the technologies for looking down are useful for the development of technologies looking up. Here's another example. This is the so-called KH9 or hexagon system. This was declassified just a few years ago. And this is at the Air Force Museum. And here's one of the hexagon satellites under construction here. So this is the key technical heritage, really, for Hubble. Now, the initial issue for the Congress was the cost of Hubble. Once the issue of priorities had been sorted out. But what actually happened was that the process of winning approval from the Congress led to what would be an unrealistic cost. And so that's a recollection by the project engineer of Hubble in the late 1980s, because there were waves of pressure on the engineers and the astronomers to get the cost down. So I'll let you read that through. This is before the issue of spherical aberration came up. I did this interview. But Hubble was actually built. There were all sorts of difficulties and problems, but they were overcome. And Hubble was being readied for launch in 1986 when there was the Challenger accident, and the launch actually took place a few years later. But that's the effectively completed Hubble at the Lockheed Missiles and Space Company in California, and you can get a idea of the scale again from the figure. That's the primary mirror of Hubble, 2.4 meters. That was built by the Perkin-Elmer Corporation in Connecticut. And the thing when we look at Hubble is, remember, the entire Hubble is really a precision instrument. I mean, it's big and it's bulky, but it's a precision instrument in which the mirror and the associated optical system has to be extremely precise, but so does everything else in the optical train. So we can get to April 1990, and finally the Hubble is launched 13 years after the Congress and White House had given approval to NASA to proceed. But problems occur fairly soon after launch. This is a star, an obscure star, Melnick 34, and it's a star image, and we should not be seeing all these strange tendrils and filaments coming off from the central image. It should be a tightly focused core. So what's happened? Well, it's a problem well known to people even who build amateur telescopes, a problem of spherical aberration, where light that hits the edges of the mirror reach a different focal point from light that reaches the mirror closer into the center. So you end up with a blurrier image than you would hope. And that caused a firestorm, in fact. And Hubble made the front cover of news magazines, newspapers. It opened nightly news broadcasts. This reference we see to NASA's 1.5 billion blunder. Never mind, come back and give the examination to NASA. Those of you who like avant-garde movies will not have seen Naked Gun 2.5. But for those of you with more eclectic tastes, may remember Naked Gun 2.5 when the characters go into what's called the blues bar. If you get the blues, you go into the blues bar. And in the blues bar, there are all sorts of pictures around the walls. There's the Titanic, the Hindenburg, there's an Edsel, there's a picture, and the Hubble, because Hubble has now transcended the normal kind of location for instruments. It's not stuck in some observatory or in the plans of astronomers or NASA centers or a contractor's plant, but it's made it into the public realm. It really has become very famous, but famous as this apparently appalling failure and a symbol of national decline. So there are all sorts of articles that were prompted by the Hubble to do with American decline. Why was Japan leading the United States, for example, and people pointing to the example of Hubble? Well, very quickly, the problem with Hubble was identified as a main mirror that was too flat at the edges, a tiny amount, but in optical terms, it was huge. And the mistake was made in the assembly of a piece of test equipment, a so-called null corrector that was used in testing the mirror. There we go. There's the primary mirror, its test chamber, and this piece of technical equipment, the so-called null corrector, was assembled incorrectly. But why was the problem not caught? Well, Hubble was what was explicitly termed as a low-cost, high-risk program. You do things once. You don't go back, and cross-checks were systematically removed from the program, or there was pressure to cut additional testing. And so when the null corrector, I won't go into the details of this, but when the null corrector was misassembled, the fault was not caught. So there's a gap that's referred to here, 1.3 millimeters. Well, that's a huge gap in optical terms. That gap should have been closer to an error of about 10 microns, instead of which there's a separation of 1.3 millimeters. And so that was huge, and that's what led to the spherical aberration. So here's one of the opticians who worked on the Hubble mirror. He was one of the people who was interviewed by the NASA General Counsel when there was a settlement between NASA and PerkinElmer, and he was asked about how comfortable he felt about the primary and how well it was working. He said he was pretty sure, and that's a direct quote from the interview with him, he was pretty sure the reflective null corrector was right. He quantified his comfort level with the reflective null corrector and primary mirror at 90%. Well, when I go to my garage and get into my Ford Focus and want to drive out of my garage, I hope that the different components of my Ford Focus are working better than at 90%, because if that's the comfort level, it's never going to move, right? And so here was a clear indication that there were issues, but the issue was not resolved before launch. There were lots of different options pursued. Cancel the program. Well, in fact, there was little traction for that. Return Hubble to the Earth, fix the mirror. that seemed dangerous because if you brought Hubble back to the Earth, it might get contaminated, and also maybe you'd never get back into space. So the solution that was made or followed was this one: redesign the main camera on the telescope. But already there was a backup that was being constructed, and also install a device that could fix the problem with the main mirror for the other scientific instruments. And in fact, this device will be called CoStar. You can see CoStar again out there in the gallery, and this camera that was specially designed to compensate for the problem with the primary mirror. That camera, the so-called Wide Field Planetary Camera 2, is also out in the gallery. When this was going on, a new institution was actually being constructed. This was the Space Telescope Science Institute in Baltimore, started from just a few offices on the Johns Hopkins campus. Now they have their own dedicated building. That was completed in the early 80s. The first director was a Nobel Prize winner, Riccardo Giacconi, who would win his Nobel Prize for work in X-ray astronomy. And many of the Space Telescope Science Institute astronomers were actively involved in figuring out what to do with Hubble. And so in 1993, there was a repair mission launched. And a lot was riding on this mission, because if NASA could not fix the Hubble, what hope was there for building a space station? If you can't train astronauts to fix something like an orbiting telescope, how could they possibly construct what was planned to be the International Space Station? But things went remarkably well. There's astronaut Kathy Thornton jettisoning a malfunctioning solar array, and then we see a couple of other astronauts at work in the payload bay of the shuttle. There's Wide Field Planetary Camera 2 being installed into Hubble by astronaut Jeff Hoffman. That's CoStar. That's not CoStar being installed, but it's CoStar being taken out. It was taken out in 2009. And as I say, CoStar is now outside. The crew also got a call from the president and vice president. But how well would things work? Well, here's a before image. Here's an after image. After the telescope had been repaired. And the point of NASA showing this was to underline the big improvement in the optical performance of Hubble, and Hubble had in fact been repaired. So that's an image produced by the European Space Agency with their faint object camera. Here's a star image before CoStar was installed, after CoStar was installed. And that's Senator Barbara Mikulski, of course. This is not 1994, but it's a little bit later. But Mikulski in 1990, when the problems were first announced, had referred to the Hubble as a techno-turkey. But in 1994, when the first images that came back from the repaired Hubble were available, she was at the press conference showing those images we just took a look at, and announced that the problems with Hubble were over. And she was arguably the most important politician or is still the most important politician in the history of Hubble. So, what about public perceptions? Well, they were transformed by things like, for example, the impacts of Comet Shoemaker-Levy on Jupiter, the famous pillars of creation, the deep field, which you heard about. Now Hubble images turn up on the covers of news magazines. No longer do we see an image of Hubble itself as a $1.5 billion blunder. Now we see the results from Hubble. And Hubble became, within a year or two, no longer a symbol of failure, but a symbol of American, in particular American technological prowess. Then briefly, I'll just cover the fifth servicing mission, because that, I think, tells us something about the level of support amongst the public. There's George Bush and Sean O'Keefe, the then NASA administrator, as I say, 2004. And President Bush announced a new space exploration vision. But that vision did not include Hubble, or at least another servicing mission for Hubble. There was planned to be one more servicing mission to Hubble, but not in NASA's planning. So Barbara Mikulski, Senator Mikulski, wrote a letter to O'Keefe, making her feelings clear. It cannot be terminated prematurely with the stroke of a pen. And so O'Keefe was on warning. Here's O'Keefe's response. Thank you for your thoughtful request. I wonder what his private thoughts were. And there was an outpouring of criticism of O'Keefe's decision. For example, in the Denver Post, there was an editorial that pointed out the public and Congress are letting NASA know they understand the real value of the Hubble Space Telescope, even if NASA doesn't. And there was a group of people who became called Hubble huggers, supporters of Hubble who, in large part, I think, due to the remarkable images that were being produced by Hubble and disseminated like the pillars of creation, have become very strong supporters of Hubble. So you can read lots of pieces in congressional testimony to do to the emails and phone calls Congress people were receiving about Hubble. And then, under the guidance of a new NASA administrator, Mike Griffin, the cancelled servicing mission was in fact reinstated. He made that decision in 2006. By 2009, Hubble was actually ailing quite significantly. It was already planned to install 2 new instruments, but 2 of the instruments that were planned to stay were both having serious problems, the Advanced Camera for Surveys and the Space Telescope Imaging Spectrograph. And so a plan was developed to actually fix them on orbit, although that had never been planned. They'd always, the instruments were always intended to be taken in or out of the spacecraft as a unit, and a bunch of other things were done as well, including replacing a key data handling unit. So, May 2009, the servicing mission goes ahead. Wide Field Camera 3, for example, was installed in the telescope. There's a visor of John Grunsfeld, the only astronaut to visit Hubble 3 times, and you can see his colleague Drew Forstall in the image, as well as the Earth behind there. Farewell to Hubble, May 2009. The view of the retreating Hubble from the shuttle. Shuttle lands. Big issue now again is how well have these various installations and replacements worked? And the answer was extremely well. And typical image of Hubble, produced by the fixed Hubble rather, antennae galaxies. This is a 2015 image of the pillars of creation, showing what could be done even in 2015, several years after the last servicing mission. And so after that very quick run through the history of Hubble, let's do our move to 2090. Let's now think, what is it we're going to read in our textbook, or favorite electronic device, or implanted chip in our brain, whatever it is, that's letting us read and think about the Hubble in 2090? Well, of course, there are the remarkable, I think, scientific results, the discoveries. Hubble becomes, in time, I think, the most famous scientific instrument ever built. It underlines the potential for astronauts and the kinds of things astronauts can do in space. So it provides a strong justification, I think, for human spaceflight. There's also a public engagement via the internet, textbooks, etc. So one of the things I wanted to do at the start of the lecture was show the world in black and white, because most of my early slides were not color, but later Hubble produces a world of color with its images. So the way that people think about the universe, I think, has been fundamentally reshaped by Hubble. But it also exemplifies what seem to me key issues in the history of science in America in the 20th century. Because in many respects, I think, the history of science in the 20th century is an American story. And why is that? I think, in part, because it demonstrates an ability, or American scientists and engineers have demonstrated an ability to manage changing scales of effort. In particular, to manage increasing scales of effort. And Hubble, as I alluded to earlier, also helped to remake the American astronomical community. So let me pick up on some of these a little bit more. Success produces success. And so what do I mean by that? Well, even before Hubble was launched, there were plans for what was called, at that time, the Next Generation Space Telescope. There were plans laid at a meeting in 1989, the year before Hubble was launched. But those plans went nowhere when Hubble was suffering from spherical aberration. But once Hubble started to produce world-class science in profusion, then plans started to pick up for what would become the successor to Hubble. And the name of the Next Generation Space Telescope was changed in 2002, and it became, and I suspect maybe one or two of you even work on this, it is the James Webb Space Telescope. And so that's the 2.4 meter Hubble mirror, that's the 18 segments of the James Webb primary mirror. Here are 6 of those segments being tested at the Marshall Space Flight Center. And if all goes to plan, the James Webb should be launched in late 2018. So, public engagement. Well, the images, I think, really have mediated between the astronomers and the public, to an extent where they can even be regarded as works of art. Change of scale. One of the most spectacular examples of this ability to manage increasing change of scale, I think, comes from the development of the cyclotron. So the first cyclotron was completed in 1931. This was invented by Ernest Lawrence, the physicist Ernest Lawrence, and built by his graduate student. And the size of the first one was about 5 inches, so roughly your hand spread out. Within a decade, they were building this beast, having gone through a number of intermediate steps. So the first cyclotron may have cost, say, $1,000. Within a decade, and this is the decade of the Depression, remember, within a decade, Lawrence is building a machine that is going to cost about $2 million. George Ellery Hale is another spectacular example of someone who can manage this increasing change of scale. So his first big observatory is the Yerkes Observatory at Williams Bay in Wisconsin. He then is the driving force behind the foundation of the Mount Wilson Observatory, which is where Edwin Hubble worked. So here's the dome of the great 100-inch telescope. And then he becomes the driver in the early days of what becomes Mount Palomar and the great 200-inch telescope on Palomar Mountain. Hubble, I think, also exemplifies this ability to manage increasing scale. Moving from instruments on V2s, which invariably smashed into the desert in New Mexico, small instruments, to the Hubble, involving thousands of engineers and scientists costing many billions of dollars and now celebrating 25 years in orbit. It also helped to remake the American astronomical community, I think. And it marked a shift from a few what you might call elite astronomers presenting to the Congress or talking with policymakers, to now community efforts, where you have an entire community of scientists who make arguments in support of astronomical projects. So in part, Hubble has helped remake what it actually means to be an astronomer. An astronomer is not somebody who just sits in their observatory or at their desk doing calculations. There is now a far greater political and wider engagement by astronomers, I think, than ever there was before Hubble. So that's the story of Hubble, and on, with any luck, to a successful increase in scale with the James Webb in 2018. Thanks very much. Okay.
Well, thank you. Thank you very much, Robert. It really was quite a tour, and also a perspective that's very appropriate for this, the last in the 4 lectures this season, celebrating and commemorating the 25 years of the Hubble Space Telescope. Any questions? Right there.
Yeah, earlier you mentioned that the defense industry had really contributed to the technology of the Hubble by the spy telescope. I'm curious, had PerkinElmer ever made mirrors for them? And if not, what was missed in the, you explained the testing, but was there something simple they could have done to avoid this problem?
You want to repeat the question, or shall I? Okay. PerkinElmer made the mirror. The mirror didn't come out right. But had they made other mirrors like that in the past, and did they come out right? And why?
They had a long history, certainly with astronomical telescopes. They built mirrors, for example, for the Stratoscope project. Remember that balloon we saw at the very start? That telescope package had a PerkinElmer mirror. Exactly what they did for the Department of Defense, I wouldn't get very far asking with my accent. But there are now memoirs that people are writing, because a number of these projects have been declassified. For example, it was the case that PerkinElmer built the optics for the KH-9, for instance, that we saw, which is also hexagon. That program was declassified in 2011, and if you go to the Air Force Museum, you can see at least a shell of a KH-9. So what could have been done? Well, there were a number of suggestions about cross-checks that were proposed, but in the earlier history of the Hubble, if I'd have had more time, I would have split the development into 2 parts. Before 1983, money was exceptionally tight, and there was an enormous emphasis on not spending more than had been allocated. And there are enormous schedule pressures as well. After 1983, it had become clear to senior NASA managers that they just could not go on in this fashion, and it really needed extra time and it needed extra money. But the mirror, the primary mirror, had been finished before that phase of the project. So the people working on the mirror were under enormous pressure to keep to their schedule and not overrun. So in that atmosphere, anybody, and sometimes this happened, anybody proposing extra tests to do rechecks of something, for example, they were just not going to get much of a hearing. So it was very difficult in that atmosphere. Now, if you want to read the technical analysis of what happened, if you just go to the web and go to Allen Committee report, you can pull that up fairly promptly. But the losing bidder for the primary mirror was Eastman Kodak. And I should mention that those of you who've been through Explore the Universe, the gallery downstairs, will have seen the backup mirror for Hubble. And that was built by Eastman Kodak. And in fact, there was a proposal to test the Eastman Kodak mirror in the Perkin-Elmer optical test chamber as an extra check. But that would have taken extra time and it would have cost extra money. And there's a memo that I can remember where this proposal was actually made, and on the side, the manager has written "out of scope!" exclamation mark. So anything that was out of scope in contractees was not going to get much of a chance to be implemented. There are a number of discrepant bits of data that, with hindsight, pointed toward the spherical aberration. But again, under the schedule pressure, under the budget pressure, there was no stopping and saying, okay, let's explain what's going on here. We need to stop. And in fact, a number of the people working closely on the mirror on a day-to-day basis did propose doing that. But they were told to, quote, cease and desist, which is a term some of you may be familiar with.
Right here.
Even though the web will be launched, are you have worries about the future of funding for space telescopes in America beyond that? Particularly because Social Security is supposed to crash around 2030.
The question is, are we worried, is the astronomical community concerned about what to do after Webb? Well, how about just making Webb work?
You know, it takes so long to build these big state-of-the-art observatories. You've got to start early, and in fact, there are already plans being laid for the successor to Webb. And the current acronym is at last. So if, in fact, you go to the Space Telescope Science Institute website, you can see some of these earlier planning studies that have already been done for at last, which will be a large optical ultraviolet telescope. So Webb is going to work in the infrared. At last is planned to work in the optical ultraviolet. So Hubble itself works in the near infrared, optical, and some UV. And so Webb won't duplicate everything in terms of the wavelengths that Hubble has covered. So the plan is at last we'll cover these additional wavelengths.
Those of you who came to the first lecture by Frank Sempolina will remember one of the proposals that he's been developing for a robotically tended instrument in the Lagrange orbit to follow Webb. Something that is an unimaginably fascinating telescope. Yes, in the green.
Why not put a telescope on the far side of the moon, and you could have a moon base and a telescope there, and do, multi endeavors on the far side of the moon?
Why not put a telescope on the far side of the moon, where you could have a whole moon base, so to speak, and operate the telescope in many, many different ways?
The idea of basing a large telescope on the moon goes back a long way. And in fact, for a time, what became Hubble, the name was changed from Large Orbital Telescope to Large Space Telescope, just because there are some astronomers who supported the idea of at least thinking seriously about putting a telescope on the moon. So the Large Orbital Telescope for a time became the Large Space Telescope to cover exactly that. So studies tend to happen on that, and then when, for example, there were plans that were laid by President, or announced by President Bush on the steps here, actually, and I'm forgetting the precise date, but round about, I think, 1990, to return to the moon, that sparked a whole bunch of planning studies about putting telescopes again on the moon. So these kinds of studies about basing telescopes on the moon tend to go in phase with these broader NASA plans.
Would there be a benefit, though? I mean, would it be cheaper on the moon?
Would it be better on the moon, a benefit?
Cheaper?
It's seen as much more, I think, much more expensive. By this point, astronomers have a preference for putting telescopes at what David was mentioning, the Lagrangian points.
And it's also zero G is much kinder on telescopes. Think of them as extraordinarily flexible, extraordinarily delicate devices. And the more kinematically rigid they are, the fewer forces on them, the better they perform.
And the moon has an
Okay.
atmosphere.
Okay. Up back there, yes, in the pink, is it? Okay, yeah, you, yeah.
One determining factor for the length of time that Hubble will be operational, and what kind of plans might there be to continue to be maintained and to be operational?
What is the prognosis for the life of Hubble, and are there plans for it to be maintained?
I don't think there are any more plans for it to be maintained, basically because there's no more space shuttle, at least space shuttle flying. Once upon a time, when I worked at the museum, there was even a thought that at some stage a shuttle would go up, get Hubble, and bring it back so it could be displayed in the museum once its operational life was over. But unfortunately, we're past that. But there will have to be something done with Hubble because it's a big object. And so, at least as I understand it, the current plan is eventually to put attach some sort of unit to Hubble so it can be safely, or can enter the atmosphere safely rather than enter the atmosphere in some random fashion and potentially rain debris on people's heads.
Not a good idea. There was a question right here.
In terms of public engagement, do you see the current crop of discoveries of exoplanets as producing a similar effect to the Hubble images in how the public engages with astronomy?
Has the recent explosion in our appreciation for the number of planets out there through the exoplanet work of Kepler had a similar impact to the incredible images that Hubble has produced in the last 25 years?
Yeah, I wouldn't be surprised, but I'm just not sure at this point. I mean, there's certainly enormous interest in the whole idea of exoplanets, in part because I think it ties in to ideas to do with alien life in some form or another. And so NASA, in fact, instituted in the late 1990s a program that was entitled Origins, precisely to kind of emphasize these sorts of projects hunting for planets, searching for life in the universe, and so on. But at this stage, I will be interested in seeing any research that anybody's been done in terms of number of hits on the Kepler website and all that kind of stuff.
Right there.
You said that CoStar, which corrected the optics, was removed. So what is correcting the optics now?
Well, what you can do is...
You want to repeat that?
Oh, yeah, sorry.
Okay. CoStar was removed, and it corrected the vision of the other instruments. And the question is, what's correcting them now?
Well, what you can do is design the optics within your scientific instrument to correct for the missed shape of the primary mirror. So when we looked at the WIFPIC 2, the Wide Field Planetary Camera 2, being installed into the telescope in late 1993, what had happened there was there were already plans for what was called a clone wide field planetary camera. And so what the engineers and astronomers did was just to redesign a number of the mirrors in the and lenses within the wide field planetary camera 2, so that they would correct for the primary mirror spherical aberration. So that was actually installed in 1993, and that sits actually out in the gallery. So exactly the same procedure was followed for wide field camera 3 that was installed in 2009, and for the cosmic origin spectrograph that was installed in 2009 as well. But COSTAR, when it was first installed, corrected the optics for the faint object camera, the high resolution spectrograph, and the faint object spectrograph by intercepting the light from the primary mirror before it entered into the other scientific instruments. But once those instruments have been removed from the telescope, there was no need anymore for COSTAR.
So we got it.
So COSTAR is also downstairs.
So you misadjusted the instruments to compensate for the misadjustment?
Yeah.
Exactly.
And then you've corrected the problem.
Exactly right. Over there.
I don't know if the person's still here, so much people ask, but somebody asked a question in the sort of pre-presentation. Asked you, how do you try to sort of convince lay people to fund astronomy and all of these kind of major projects in an era when everyone knows all the funding is tight? And then, we see this absolutely marvelous presentation that you gave us today on the work of Hubble over 25 years. And I really tried to sort of redact the politics, so I apologize in advance if I didn't do a good job. But I really I always sort of get the feeling that there's a sort of hidden premise when people question this work, that there's some other way that it might come about, other than the way that it always comes about. Like somehow other than by means of NASA, how else would it come about? Because I don't really believe that people are saying, we don't really want to add to the corpus of human knowledge. We don't really care what's out there. We don't really want to see those pictures. We don't really want to confirm the data. We just want it to, I don't know, we just want it for free or something.
What are you actually asking us?
I'm asking the answer that you gave, and I'm not saying that it wasn't a fine answer, but I wonder if you would agree or not with what I'm saying, that really people want the work to be done. They do. It's not that they don't want it done, but it's literally just, it's hard to write the check at the end of the day.
Right, and I think the people within the astronomical community now understand that much better than they did in the early 1970s, for example. So you now have community efforts to try and underline the importance of particular kinds of astronomical projects. And so there's far more willingness by astronomers to engage policymakers, for example. And again, as I say, it's not just a few astronomers doing this. It's a much broader, I think, community-based effort. And I think astronomers have been much more successful at that kind of effort, in part because they have the wonderful images to show, than, say, high-energy physicists. Because the story I've told here, I could have given a version of this with the story of the superconducting super collider, which some of you may remember, that was cancelled in, I think, 1994. $2 billion had been spent on the superconducting super collider, but it ended up being cancelled. And in part, that was because I don't think the high-energy physicists organized in the same sort of fashion as the astronomers did in the mid-1970s, when they saw that what would become Hubble might not get approved. And so that was very much, I think, a learning experience for the astronomers, where the high-energy physicists had got so much support over the decades after World War II, they almost took it, I think, for granted that money would keep on coming. But now there's much more willingness, as I say, certainly amongst astronomers, to actually work at those kinds of issues and to emphasize the value of basic science for members of the public in terms of this kind of public engagement, broad public engagement with science, as well as the importance of various issues for policymakers like American leadership in certain areas in science, and as well as the usual kinds of arguments about the possible spin-offs that can emerge from these endeavors.
Yeah, it's one of the fascinating things. Astronomers have been pretty much at the head of the, or on the leading edge of the curve, understanding that they had to organize and clearly state what it is they wanted, starting in about 1960-61.
Yeah, so that's a really key point that David made. The astronomers, every decade or so, go through this difficult process where they come up with priorities. What do we want as our number one priority or our number two, and so on? That's not easy because you have hundreds of members of the astronomical community meeting, thrashing things out, trying to come up with a list of priorities so that they can all get behind their number one priority and their number two priority. And it's been, I think, actually very effective for astronomers in meeting the needs of policymakers. Whereas if you just do things in a kind of semi-random basis, where you have a group of people interested in this project, a group of people in that, then by the time the policymakers are looking at what's happening, all of the projects they see invariably have really great science. So why distinguish between different ones? It's much better if the relevant scientific community can make the hard decisions themselves and say, here's why we think this should be the number one priority.
That's right. Okay, we can take 3 more, hopefully quick questions up there. Yeah.
Isn't it true that even with the uncorrected spherical aberration, Hubble is still outperforming ground-based telescopes, and was in fact the best telescope ever made even before the correction was applied?
The question is, or the statement is, isn't it true that even without the correction, Hubble was still one of the most, if not the most powerful optical telescope available to astronomers?
For some classes of observations, I think the astronomers would have agreed with that, with suitable computer processing of images. But for very distant objects, which was often seen as the kind of key driver, at least in the early days of Hubble, it was just devastating, the spherical aberration. And I don't think NASA would have paid, and if the idea that maybe, okay, Hubble's working at least to some extent, let's just leave it. I don't think NASA would ever have paid, and the US taxpayers would ever have paid $2 billion for a telescope as Hubble was when it was first launched in 1990. And they certainly wouldn't have paid for 5 servicing missions, it seems to me, if the idea was, well, you don't actually improve it.
There was one right here, and then one over here. Yes.
James Webb telescope will not be orbiting Earth like Hubble. Why is that? What's the fact?
Why won't the James Webb orbit in low Earth orbit like the Hubble? Why is it sitting 1.5 million miles beyond the moon in a semi or quasi-stable orbit called a Lagrange point?
The Webb is going to work at infrared wavelengths between about 1 and 28 microns. And the problem about low Earth orbit for infrared telescopes is that they go through these cycles of intense heat and cold. Because you're on the daytime part of your orbit, then you move to the nighttime part. And so you want really to try and keep your telescope as cold as possible if it's an infrared telescope. Because what can happen is if you've got a hot telescope, it's giving out lots of heat. And so your light detectors, infrared light detectors, are going to get messed up by the warmth of your telescope. So you want to be where you can be cold, and also arrange for the sun shield of the James Webb to block the solar light. So you've got a steady environmental condition, whereas one of the issues for Hubble was this cycling in low Earth orbit. But because the wavelengths of Hubble are different from those of Webb, then Hubble could accommodate that. But Webb is, as I say, an infrared instrument, and so it poses different demands.
And the last question here.
Would you care to comment on the very sophisticated image processing techniques used on the Hubble images to add color and to highlight certain features and such? And do you think that has been a factor in the public engagement? Had we been looking at black and white images, would the Hubble have had as pronounced an effect?
I doubt it. Oh, so
What am I, a potted plant?
earn your money, David. Earn your money.
No. The question is, given the very highly sophisticated processing, image processing, this is like advanced super Photoshop, or should I say Corel for the rest of us, without the introduction of that color and the incredible dynamic range that you get from the dye transfer, the old dye transfer process in producing color, would the Hubble have had the same impact? Is that fair?
I don't think it would. And I think Hubble has had a remarkable impact because careful thought and effort has gone into the construction of those images for public consumption. And there's a wonderful book on those images by a historian of art called Elizabeth Kessler. And let me just mention that she was another of the people who've benefited from support from the Smithsonian. She was here on a fellowship. So I would highly recommend Elizabeth's book as a way to really understand what's going on with those images. And so she points to the combination of, I think it's engaging the senses and reason, why they're so powerful. You know, if you think about why is it that the Pillars of Creation is a really striking image, her answer is it's because something like the Pillars of Creation engages our reason and our senses in these remarkable ways. And the
Our visual traditions?
Because, for example, she points to linkages between at least some of the Hubble images that have been produced more for the public consumption rather than just strict scientific analysis between those kinds of images and paintings of the American West in the 19th century, for example. So some of the same kinds of conventions that you see in some of these remarkable 19th century American West paintings, you also see in play with some of the Hubble images. But it's an incredibly colorful world that's being created by Hubble. And it's so different from the kinds of textbooks that I can remember getting when I was an undergraduate, where you have these black and white images taken from, say, the Hale observatories. You know, you get black and white galaxies in maybe a few color images, but those images now are so readily available via the internet, all different kinds of other social media, that not only are they highly colorful, but we have so much ready access to them as well. You know, go tonight to the Space Telescope Science Institute website. Look through some of the images. I mean, it's really quite startling to see the range and the power of so many of those images, I think. And that has been a clear, I think, link between the public and what used to be this kind of elite enterprise where you have a bunch of people on mountaintops doing this stuff, and then they would send you these black and white images that were, you know, not great, you know, but they were the best that were going. So they've effected, I think, a new relationship between an astronomical enterprise and the general public. And that also has a political link, of course, because as we saw with the outcry when people got cross at NASA for cancelling the final servicing mission, it leads to people sending emails and so on. So there are constituency builds for Hubble as well by doing that.
And on that point, I want to thank Robert again and thank all of you for wonderful questions. And I should say, Beth Kessler's book is called Picturing the Cosmos. It's available from the University of Minnesota Press. And by that segue, Robert and I will be signing copies of our book, Hubble, Imaging Space and Time, out at the welcome desk after the talk. But it is clear, and there is a spectacular event going on in the sky over the last few days and weeks, and that is a conjunction of two of the brightest planets in the sky. And unless it's thundering right now, I welcome you to go out to the observatory and have a look at the conjunction of Venus and Jupiter. Thank you very much for coming tonight. And thanks again to our supporters, and see you next year.